Hello and welcome to the instructional video on section 5.4 for Math 172, the graphs of sine functions and cosine functions. And let me call this up here on the screen. The last time we talked about the trigonometric functions, sine, cosine, tangent, cotangent, secant, and cosecant, algebraically, and now we're going to look at the graphs, first of all, in this lesson of the sine and cosine functions, and the next lesson, section 5.5, is going to be about the graphs of the other trig functions, tangent, cotangent, and secant and cosecant. So this lesson is focusing on the sine and cosine graphs. And we talked last time about how trig functions are periodic. Sine and cosine functions, for instance, as long as it's just sine of x or cosine of x and no coefficient in front of the x, then the period of such a function is 2 pi. The function completely, precisely repeats every 2 pi units going either to the left or going to the right along the x-axis, horizontally speaking. And that means that each period of the graph looks the same regardless where you are horizontally on the x-axis. So let's look at this here. Let me bring this up. Yeah. So you've perhaps heard the expression of a sine wave, and that's the description that's used scientifically to speak of various different wave formations, for instance, electromagnetic waves like light waves, radio waves, such as that. Various different kinds of waves travel in a pattern that actually is a sine wave. So it's actually the graph of some kind of sine function. Excuse me. So it's also known as a sine curve. In mathematics, we don't always call it a sine wave. That's more of a scientific term. Sine curve is more of a mathematical term for the name of the graph of a sine function. And each and every period of the function, that is every portion that's 2 pi units wide of the graph of the function, is called one cycle of the sine curve. One cycle, therefore, is also equivalent to what's also called one wavelength. One wavelength along the curve. One cycle or one wavelength is the same thing. And we're going to see, for instance, how the shape of the sine curve and the cosine curve, the shape is exactly the same. It's simply a horizontal displacement one way or the other from the other one. Each one, if one is moved horizontally just the right amount, then the graphs would be precisely right on top of each other in that they have exactly the same shape. Just a different horizontal orientation in the plane. So the very first one of these, sine function, let's look at that first. The portion right here of the graph that's in black is one full period. It's from x equals 0 to x equals 2 pi. And if you note, starting at x equals 0, the graph goes upwards. The graph is increasing up to a peak right here, and that's the maximum point at x equals pi over 2, or as we're used to thinking, 90 degrees. But remember that with your trigonometric functions, we're not going to use degrees. We will always use radians with our trigonometric functions. The x values will always be in radians, and so you want to have your calculator set to radians. Be careful about that too. So we reach a peak on the graph up here where y equals 1 when x equals pi over 2, and then once you pass x equals pi over 2, moving to the right, the graph is now decreasing, comes back down, has an x-intercept at x equals pi, keeps on going down, but less and less steeply, till finally the very bottom, and that's at x equals 3 pi over 2, and finally there you start increasing again up to x equals 2 pi. You have another x-intercept of the graph. So from x equals 0 to x equals 2 pi, there's actually 3 x-intercepts. And there's one maximum point at where y equals 1 and one minimum point where y equals -1. And then thereafter, if you follow the graph of y equals sine x to the left, it simply follows that same pattern we just traced out between 0 and 2 pi. It goes on and on forever to the left and on forever to the right in that same wave motion. Never changes, never alters in any way, just keeps on going forever to the left and forever to the right. So, as we spoke last time, the domain, therefore, of the function y equals sine x is all the all the values of x that have a meaningful output for sine x, and that's all values of x, period. From negative infinity to positive infinity, all values of x are in the domain of y equals sine x. There's no limit to its domain whatsoever. But there's a very, very limited range. You're seeing the entire vertical range of the function right in front of you here. It's exclusively bounded in between y equals -1 and y equals 1. Y does go up to actually equal 1, and it actually comes down to equal -1 over and over and over again to the left and to the right. But it never goes above y equals 1, and it never goes below y equals -1. It's exclusively bounded, vertically speaking, in between and including y equals -1 and y equals 1. And cosine x is the same shape, just horizontally displaced by pi over 2 units. So this next one right here, just down below the graph of y equals sine x, is a portion of the graph of y equals cosine x. And you see from x equals 0 to x equals 2 pi, it is a full period in that if you were to go to the left of that or go to the right of that, it would simply repeat the same pattern that's present between 0 and 2 pi. But notice it's not in the same pattern, in the sense that at x equals 0, the y equals sine x function is increasing as you go to the right, but at x equals 0, the cosine function is decreasing from its extreme maximum value of y equals 1, and it comes down to y equals 0, has an x-intercept at x equals pi over 2, and keeps on coming down just less and less steeply to the very bottom point here, y equals -1, at x equals pi. And then when x equals 3 pi over 2, it's back up to an x-intercept, so y is 0, and keeps on going up just less and less steeply to the maximum point where x equals 2 pi and y equals 1. Now let's consider these values in light of what we spoke of in the previous lesson. For instance, when you're going around the unit circle and examining the values of sine and cosine, at the 0 radian angle, the sine, if you recall, is 0 because the sine represents the vertical displacement above or below the x-axis. But there's no displacement at all, so it's right on the x-axis, y equals 0, so the sine is 0. And that's what you see on the graph here. When x is 0, sine x is also 0. And when x is pi over 2, that's where you're up at the top of the unit circle. You've moved around, as you recall, counterclockwise. You've gone around a fourth of a circle from the starting point on the positive x-axis at the point 1, 0. And going around the unit circle then counterclockwise, you come up to the top of the circle at pi over 2 radians. And that's at the top of the circle, you reach the point 0, 1, and so yes, the y-coordinate is 1. And as you continue around the unit circle, going from pi over 2 to pi, you're now passing down through quadrant 2 on the unit circle. The y values, of course, decrease as you approach the x-axis, And finally, when you get to pi radians, you're right back down on the x-axis on the unit circle, and yes, y is 0 and sine x is 0, and that's what you see right here in the graph. And of course, at 3/4 of the way around the unit circle, you're at the bottom of the unit circle, and y is -1, and continuing on for up to 2 pi, you're back where you started from. You've made one full circle around the unit circle, back on the x-axis, y equals 0, and so sine x equals 0 there also. And cosine x is of the same overall pattern, it's just displaced 90 degrees. For instance, if you look at the graph of y equals sine x up above here, the black portion of that graph, and now mentally imagine moving that down to superimpose it on top of the cosine x graph. For instance, you could take the leftmost point here of this black curve and superimpose it right here at the point -pi/2, 0. That would be the starting point, for instance, and then you'd go up and down and all the way down to the bottom and back up again, and that would be marking out this black curve if it were superimposed onto this one down here. And so that's what I was meaning a while ago when I said you could take either the sine curve and superimpose it on top of the cosine curve simply with a horizontal shift. In this case, horizontally shifting it pi/2 units to the left will cause the sine x graph to match up with the cosine x graph. Or you could take the cosine x graph and translate it to the right horizontally, so a horizontal shift to the right of pi/2 units, and the cosine x graph then would coincide with the sine x graph. So we could take this cosine x graph here from the top down and back up to the top again, take that whole black section, slide it up here to the sine x curve, and start it right up here at the peak of the sine curve, coming down and back up to here again, and it would be a perfect match. The entire infinite number of points would match up perfectly. What that means is, if you recall from the pre-calculus algebra course, that it actually is a horizontal shift, one way or the other, whichever way you're going, horizontal shift to the left or to the right, and that's accomplished by modifying the input variable of the function by adding or subtracting the appropriate amount. If you want a horizontal shift to the right, if you recall, you subtract something from x and then take the function of it. If you want a horizontal shift to the left, you add something to x and then take the function of it. So for instance, with y equals sine x, if we want to superimpose it on the cosine x function, we have to have a horizontal shift to the left of pi/2. So we could say this, that the sine, this is actually just sine of x, clean and simple. But if we took the sine of x plus pi/2, the sine of parentheses x plus pi/2, close the parentheses, that would exactly equal cosine x. And that's actually an identity that you saw a while back in a previous section, that cosine x equals sine of parentheses x plus pi/2. I'm pretty sure you had that in the previous section, but let's bring it up now either way. Similarly, you could say, since cosine, the graph of cosine can be shifted to the right pi/2 units to be identical to the sine of x graph, we could say that y equals cosine of parentheses x minus pi/2 is equal to sine x. So cosine of parentheses x minus pi/2, close the parentheses, is the same as sine of just x. So what we're doing now is talking about the graphs of the sine function and the cosine function, and also in light of concepts you've used in your previous pre-calculus course, things like horizontal shift to the left or the right. We're also going to be talking about vertical shifts up and down. We're going to be talking about intercept points, x-intercepts and y-intercepts, and maximum and minimum points, and intervals of these functions wherein the function is increasing versus other intervals where the function is decreasing. So those are some of the concepts from the previous pre-calculus course that are going to be relevant in these two sections about the graphs of the trig functions. If you wanted to graph one of these functions strictly by hand, perhaps the simplest way to do it is, as they point out right here, take a piece of paper, put your x and y axis down, put your scale on the axes, and then figure the points where y is going to be 0, that's going to be the x-intercept points. Figure where x is 0, that's going to be your y-intercept point. Figure the highest points of each graph, the maximum points, and the lowest points, the minimum points. And when you do that and plot those points, then you can, so to speak, come back by hand and draw in this curve as they have here. For instance, if you plotted these 5 dark points here, 1, 2, 3, 4, 5, if you plotted those 5 points, then you could come back and just loosely sketch by hand that curved graph in between there. And for instance, if I asked you to do something like this on the midterm or the final and sketch a graph of something, just doing it by hand like that and loosely sketching the graph, approximating as best you can, that's perfectly fine. That's okay. So let's look at what we can do with this right after we speak of some of the basic aspects of these two functions. On the next page of your text is a pretty convenient little box right here. It's one of these parent function boxes like you saw in previous chapters in the other course. The library of parent functions for sine function and cosine function. And the parent function for each of these is very simply just y equals sine x and y equals cosine x. And then we're going to do lots and lots of variations on a theme, so to speak. For instance, y equals sine of 2x, or y equals cosine of negative 3x, or y equals negative 5 times the sine of 2x plus pi, in parentheses, sine of parentheses, 2x plus pi, close of parentheses, things like that. All sorts of variations we're going to be doing here. But these are the two basic functions for sine and cosine, just y equals sine x, y equals cosine x. And as we've been speaking, let's sum this up here together using this useful box here. The domain of both the functions is infinite without any exceptions, from negative infinity to positive infinity for both functions. The range is the same for both functions, is very limited, between negative 1 and 1, and including both the points negative 1 and 1. The period for both functions is 2 pi. So no matter where you start on the graph, you can pick any point randomly on the graph and move 2 pi units to the right. If you pick any point on the graph, move 2 pi units to the right, the y-coordinate will be the same. Doesn't matter where you go. You can go from a minimum point to minimum point, from maximum point to maximum point, from x-intercept, well, you have to jump over the one in the middle, but you go 2 pi units to the right, and the x-intercept will not only be an x-intercept, but the graph will be going the same direction also. But you can pick any point in between. You can pick a point right here on the sine function, go 2 pi units to the right. You'll be exactly on another point on the sine function with exactly the same y-coordinate. For the sine function, the x-intercepts occur at multiples, all the integral multiples of pi. So the negative integers times pi, the positive integers times pi, and even 0 times pi, which is of course 0. So at all those values, like negative 3 pi, negative 2 pi, negative pi, 0, pi, 2 pi, 3 pi, 4 pi, etc., at all those points, the sine of x is going to be 0. And there's one y-intercept, 0, 0. So when x equals 0, y equals 0. The y-intercept is the origin. And remember, a function cannot have more than one y-intercept, because if it did, it would violate the vertical line test, and so it would not be a function. And technically speaking, the sine function is an odd function. It has symmetry across the origin. And the cosine function then has its x-intercepts separated once again by intervals of pi, but starting at pi over 2 instead of starting at 0. So it's pi over 2 plus all the various multiples of pi. Pi over 2 plus pi, pi over 2 plus 2 pi, pi over 2 plus 3 pi, pi over 2 plus 4 pi, etc., or pi over 2 minus pi, pi over 2 minus 2 pi, pi over 2 minus 3 pi, etc., etc. And the one and only y-intercept occurs, of course, when x equals 0 by definition, and it's at y equals 1. So 0, 1 is the y-intercept. And the cosine function is an even function. So that means it has symmetry across the y-axis. If you were to fold the graph of the y equals sine x function across the y-axis, it would match up on either side, the right side folding on top of the left side, or the left side folded over onto the right side. It would match up perfectly because it's an even function. Now let's pull up another utility here. I'm going to take us to the online graphing calculator known as Desmos, and many of you are familiar with this. We use this quite a bit in the pre-calculus algebra course, and we will use this also, perhaps not as much, but we will use it some also in this course. So this is a really nice program here. If you haven't seen this before, it's really fantastic. It's desmos.com, desmos.com. It's a free online graphing calculator that's quite powerful, quite able to do many different things. You can, I think, pay a monthly fee and access even more features and all kinds of neat stuff that the Desmos people keep creating and coming up with. But even just using the free stuff is fantastic. So, for instance, we can graph y equals sine x right here, and let's do that. I'm going to hit y equals, and then I come down here to the bottom functions, and yes, it's already on trig, so I'm going to click on sine and just put x. And I will close the parentheses. It's sort of optional, but let's do it. There's the graph of y equals sine x right in front of us, several different periods of it. And once again, starting at 0, 0, the graph is going up. It reaches a peak at y equals 1, and that's actually at pi over 2, which is, pi over 2 is approximately 1.57, and then comes back down here at pi, about 3.14, has an x-intercept, goes below the x-axis down to the minimum point at 3 pi over 2 and back up to 2 pi, about 6.28. It ends its period that was started at x equals 0. And then going to the right forever and going to the left forever, it keeps repeating that. And let's change the scale on this and look at this a little bit. I'm just turning the little button on the mouse here, and you see how it literally goes off to the right and to the left. Yes, forever. No matter what scale you use, you can see this. Pull it back down here. Okay, I'm coming back to more like what we started with. So that's y equals sine x then. Okay, now let's also add on to here on the same set of axes y equals cosine x, and I'm going to hit y equals and come down here to the functions and pick up cosine, x. And now we have both of them graphed on the same set of axes. The sort of orangish reddish one being the sine graph and the more bluish one being cosine graph. And I trust you can see they really are following the exact same curve, the same shape. One is just horizontally translated from the other. So, for instance, scientifically in physics, we'd say these two waves have the same wavelength, the same period, but they have a different phase shift. They're out of phase with each other. So now let's start playing with this a little bit. Let's make some variations here, like y equals sine of 2x, and see what happens. And I'm going to delete the cosine x now, so we just have the two sine functions. Perhaps you recall, if you modify the input variable of any function, you create, like multiplying it by any number, you create either a horizontal stretch or a horizontal shrink. And since I've multiplied the input variable x times 2, then that causes a horizontal shrink of a factor of 1/2, 1 over that number, 1/2. And so now the period of this green function is just pi. Just like starting right here and just going to pi, it's got a full, from 0 to 3.14, it's got a full period, up, down, and back up again. If we did y equals sine of 4 pi, then the period would be only 1/4 as much, pi over 2. So let's do that. Y equals sine of 4x. And let me even get rid of the 2x now to make this more clear. There we go. So now we have y equals sine of x, the broad one sweeping across here, and the y equals sine of 4x going back and forth, up and down really fast, so to speak, 4 times faster. In fact, one period of the original sine x from 0 to 2 pi over to here, that's one period, back and forth there, has actually 4 full wavelengths of the sine of 4x. There's one wave, 2, 3, 4, precisely ending where the first single wavelength ended for y equals sine x. So putting a number in front of the x causes the wavelength to be shortened by that factor. That's called a horizontal shrink. If we go the other direction, like y equals sine of 1/2 x, you perhaps can figure this out. That's going to double the wavelength, double the period. That's a horizontal stretch. Now let's get rid of the 4x. So again, we still have the original y equals sine x, but now we have sine of 1/2 x. The period of that is now twice as long. So instead of 2 pi, the period is 4 pi. And let's look at that now. So here's our original y equals sine of x. The first two periods going, there's one period, and here's two periods ending at 4 pi. But the y equals sine of 1/2 x, one full period goes all the way up, down, and back up again. It takes 4 pi units along the x-axis for one period, one cycle, one wavelength of sine of 1/2 x. So that's how the horizontal stretch and horizontal shrink works. Now what if we simply multiply the function by something? Let's go back to the sine x function now exclusively and put a multiplier in front of the whole thing, like y equals 3 times sine x. And you probably imagine what this is going to do. It's just going to create a vertical stretch by a factor of 3. So wherever you had an x-intercept before, you still have an x-intercept. And the difference is the altitude that's going up 3 times higher and going down 3 times farther. So you have x-intercept here, 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 exactly the same places for y equals sine x and y equals 3 sine x. The difference is the amplitude of the function, the amplitude of the waves, how far up and down each wavelength is cycling up and down. And so here's how we use that actually technical term of amplitude. The amplitude is the distance from the middle of the wave, vertically speaking, from the middle up to the top, or from the middle to the bottom. And since it's a distance, the amplitude is always positive. In this case, for y equals sine x, its standard amplitude is 1. It goes from the middle of its wave up to y equals 1, goes from the middle down to -1, so its amplitude is 1. But the amplitude of y equals 3 sine x is 3. What if we had y equals -2 sine x? You might recall that's going to create a reflection across the x-axis, the negative sign is. Aha, now there's that one. Now notice y equals sine x starts at the origin and of course goes up. Y equals 3 sine x starts at the origin and goes up 3 times steeper. But y equals -2 sine x starts at the origin and goes down. It's actually the same as y equals 2 sine x, except reflected across the x-axis. So everywhere where it would have gone up, it now goes down, and everywhere where it would have gone down, it now goes up. But the period is still 2 pi. No change to the period. In fact, all these 3 right here all have the same period of 2 pi. No change to the period because there's no coefficient in front of x other than 1. Now, what might be interesting here is to just do sine x and negative sine x. Let's look at those two. There you go. So y equals sine x, of course, is the one that starts at the origin and goes up. So the one coming down here is y equals negative sine x. It's literally a reflection of the y equals positive sine x reflected across the x-axis, horizontally, forever to the left and forever to the right. And what would happen then if we add something to x? We looked at this, we discussed this a while ago. If we had, for instance, y equals sine of x plus pi over 2, and I'm going to pick up my pi number down here so it's truly pi and not just an approximation. Click on the number right down here. Pi divided by 2, close the parentheses. So now, once again, the y equals sine x is the one that starts at the origin and goes up. But now y equals sine of the quantity x plus pi over 2 is shifted half a pi, so to speak, to the left. So instead of starting at 0, 0 and going up and down, it starts at negative pi over 2 and goes up and down. So the graph, because it has a modification to the input variable x, not by multiplying it, but by adding a number, that creates a horizontal shift. Not a horizontal stretch or shrink, but a horizontal shift. And since we've added a number, it creates a horizontal shift to the left. If we subtracted a number from x, it would create a horizontal shift to the right. And finally, I want to graph one more thing and make use of this. Let's go back and also graph y equals cosine x. Now, all 3 graphs are there graphed. They're all right on the same set of axes, but we can only see 2 of them. And why is that? It's because the second and the third one are superimposed precisely on top of each other. This green one now, y equals cosine x, is perfectly superimposed point for point for point on top of y equals sine of the quantity x plus pi over 2. We said a while ago that those two would graph the same, and now I'm having the opportunity to show this to you, that they truly do graph the same. They are precisely the same graph, not just close, but exactly the same. Okay, now let's look at one more thing here. The only possibility we have not yet considered is what would happen if we add or subtract a number outside of the sine x expression. So what if we graph, for instance, y equals sine x plus some number? Let's do that. This is going to create a vertical shift. Say y equals sine x plus 2. So now you have the entire graph. It's not stretched or distorted in any way. It's simply translated or shifted upwards, maintaining the exact same form, the exact same pattern, the exact same shape, except translated 2 units vertically straight up above the original graph. So y equals sine of x and then plus 2 is simply a vertical shift up 2 units from the original y equals sine x graph. It still has the same amplitude. The amplitude of the graph is the absolute value of the number in front of sine of x or in front of cosine of x, and the number for both of these in front of sine of x, of course, is the invisible 1. It's understood to be 1. So the amplitude of each of these is the same. It's both 1. No change to the amplitude. No change to the period. The period of this one, it starts at 0, 2, and if you go 2 pi units to the right, it's back at y equals 2 again, and one full period has transpired. One full cycle, one full wavelength, from x equals 0 to x equals 2 pi, about 6.28 roughly. So the period is the same. The amplitude is the same. The phase shift, all that is the same. We got to talk about that specifically. But what is different is the altitude of the graph. It's been vertically shifted up 2 units. And now let's go back and make use of the text once again to talk a little bit more about a couple of these things I just mentioned with you. Okay, some of these key terms. Let's talk about this. Amplitude of sine and cosine curves. The amplitude of a graph like y equals a times sine of x or y equals a times cosine x, the amplitude is always going to be the absolute value of a. It's always going to be whatever value a is. If a is positive, then the amplitude is just that number. But if a is a negative number, then we say the amplitude is a distance, so it has to be positive. So you just take the negative number that's in front of sine or cosine, turn it into a positive number, and that's the amplitude. So if, for instance, if you had y equals negative 7 sine x, the amplitude would be 7. And the amplitude of these represents half the distance, half the vertical distance between the maximum y value and the minimum y values of these two functions. And it's given by the amplitude as the absolute value of a. So amplitude's pretty straightforward. You can change the amplitude by changing the number in front of sine x or in front of cosine x, and that creates vertical stretch or vertical shrink. And now the period of sine and cosine functions is determined by the coefficient of x. by the coefficient of the x term that you're taking the sine of or taking the cosine of. So let b be any positive real number. So it can't be 0 and it can't be negative. But b being any positive real number, then what we call the period of these sine and cosine functions, like y equals a times sine of bx and y equals a times cosine of bx, the period is always given by 2 pi divided by b. So what does that mean? Well, the standard period when b equals 1, when it's the invisible 1, the period is just 2 pi over 1, it's just 2 pi. But as soon as you put a number greater than 1 in front of x as its coefficient, then you're dividing 2 pi by that number to get the period, and since it's greater than 1 and it's in the denominator, it's going to shrink the period. But if you put a coefficient of x that's less than 1, then the period is 2 pi over that number that's less than 1, and whenever you divide by a smaller number, you get a larger answer, so that increases the period, as we saw just a few minutes ago with the examples in Desmos. So horizontal shrink is created by putting a number greater than 1 as a coefficient of x, and a horizontal stretch results when you multiply x by a coefficient that is less than 1. And so now let's talk about what if the entire curve itself keeps its same shape but simply shifts to the left or shifts to the right. Then in that case we call it a phase shift. And this is kind of a new term, so let's talk about this. If we have a function written like this right here, like I'm highlighting with the mouse, y equals a, determining the amplitude, times sine of, in parentheses, not just bx, but sine of bx minus c. Okay, new pattern here. Y equals a times sine of bx minus c. And we know the period of this. We know the amplitude is the absolute value of a. We know the period is 2 pi divided by b. And with this having the minus c here, that creates a horizontal shift, and the horizontal shift is going to be in the amount of c divided by b. So that's the phase shift. The phase shift of this y equals a times sine of bx minus c, the phase shift is c over b. That's how much it's shifted from what it would have been if it was just y equals a times sine of bx. So here's your overarching rule for phase shift. The graphs of y equals a times sine of bx minus c and y equals a times cosine of bx minus c, they both behave similarly, have the following characteristics. Assume that b has to be positive. The amplitude is the absolute value of a. The period is 2 pi over b. And the phase shift is c over b, and, which it should say here, I wish it did, and it's way up here, but anyway, the left and right endpoints of a one-cycle interval can be determined by solving the equations bx minus c equals 0 and bx minus c equals 2 pi. So regardless what kind of period or phase shift or anything you're dealing with some complicated sine or cosine function, you always use the 0 and always use the 2 pi there. That's the standard, because that's the regular period from 0 to 2 pi of the parent sine function and the parent cosine function. So you can simply solve that equation, whatever bx, b and c are, the bx minus c, set that equal to 0, and bx minus c and set it equal to 2 pi. And when you do that, the x value that you get in both those cases will be the left endpoint and the right endpoint of exactly one period, one wavelength, one cycle of your graph. And that's quite helpful to know that. Like for instance, this one right here, analyze visualize the graph of y equals -3 times cosine of 2 pi x plus 4 pi. Well, the amplitude is 3 because the value of a, the coefficient of the cosine expression, is -3, and the absolute value of -3 is +3, so that's the amplitude. So it's going to be a distance of 6 from the very top of the graph to the bottom of the graph. The amplitude is 3. The period then is 2 pi over b. Well, in this case, in this function, the number in front of x, the coefficient of x, is exactly 2 pi, so that is b. And remember, the period is always 2 pi divided by b, so it's 2 pi divided by 2 pi, so therefore the period of this function is exactly 1. So every single unit along the x-axis to the left and to the right, you'll have a full wavelength, a full cycle of this function. And then if we set bx minus c equal to 0 and bx minus c equal to 2 pi, now let me make a point here. With this 2 pi x plus 4 pi, you've got to catch this now. The 4 pi is not c. Remember, the standard form is bx minus c. So c is the number being subtracted from the x term. Well, here it's 2 pi x plus 4 pi, but in terms of subtraction, that can be equally rewritten as 2 pi x minus parentheses -4 pi. So actually c here is -4 pi. b is 2 pi and c is the number being subtracted from 2 pi x, so it's 2 pi x minus a -4 pi. So anyway, 2 pi x plus 4 pi, that is bx minus c. That equals 0, and it also equals 2 pi. Solve for x in both cases, and you can do the simple algebra, and you get x equals -2 and x equals -1. And notice, horizontally speaking, the difference between x being -2 and x being -1, of course, is exactly 1, which confirms what we discovered above, that the period truly is 1. In fact, let's go ahead, before we do the very last thing about vertical shift, let's go ahead and graph this one right here in Desmos and look at it. So y equals -3 times cosine of 2 pi x plus 4 pi. And let's confirm this. We should have a wavelength that starts at x -2 and ends at -1. It should have an amplitude of 3 and a period of 1. So let's experiment with this a little bit here. Delete both of these. Y equals negative cosine of 2 pi x. Well, that didn't work. Let's get rid of that second parentheses there. Yeah, 2 pi x plus 4 pi, close the parentheses. There we go. Oh, sorry, it was -3 times that. There we go. All right, so now let's see what we have. -3 times cosine of 2 pi x plus 4 pi. That's the function that was in text in that example problem. And yes, this does have an amplitude of 3. It's going all the way up to +3 and down to -3. So starting at the middle and going up or going down, yes, the distance is 3. So the amplitude truly is 3 as it's set. And the period is supposed to be 1. So cosine function from way down here at -2, and then you go one full period all the way up and back down again. Yes, and you can see Desmos is highlighting it for us. That point is -1, -3, and the previous point was -2, -3. So actually there is a period, a full wavelength, a full cycle, full period, every 1 unit to the left or to the right. So x -3, -2, -1, 0, 1, 2, 3, each of those is a full period of the function. So yes, we've confirmed graphically that the period really is 1. And the phase shift is C over B. Well, the C is negative 4 pi over B being 2 pi. So negative 4 pi over 2 pi is negative 2, which means that the cosine function, for instance, is right on 0 at negative pi over 2. That's about negative 1.57. So with a phase shift of negative 2 at negative 3.57, it should be on 0 again, and I think that's what we're seeing here. Well, negative 3.75. So there is a phase shift. We do have a period exactly equal to 1. We do have the amplitude equal to 3. And once again, I really want to emphasize to everybody, Desmos is just such a fantastic tool. It's actually easier to use a lot of times in your graphing calculator, because on that you have to set the window and then adjust the window so laboriously. It's not that simple. You can do it, but it's kind of tedious. And here we can, for instance, adjust the window just scrolling the mouse, or just grab this thing and just grab, well, yeah, there we go, and slide it. You can move it however you want. That's really nice stuff with this. And the only other thing we haven't talked about, and I guess this is as good a one as any to do it, is vertical shift. Well, we've mentioned that, but that's the last point. If you have, for instance, y equals negative 3 cosine of 2, well, this is taking some time just to enter all this in here, plus 4 pi, close the parentheses, and now let's say minus 3. Well, what do we have now? What do we have? We have our original function, which was centered, vertically speaking, right on the x-axis, and went 3 above the x-axis and 3 below it for an amplitude of 3. Well, this one still has an amplitude of 3, but it's because we've created a vertical shift downwards of 3 by subtracting 3 outside the parentheses here at the end, minus 3, and some of your textbook problems and homework problems and all, they'll do the plus 3 or minus 3 in front of the sine or cosine function. Anyway, I don't usually do that, but the text does. It's not a big deal. But anyway, subtracting 3 drops the whole function, vertically speaking, 3 units. Still has the same shape, the same period, same phase shift, everything. It's just dropped down to 3. So now the center line vertically of this function, instead of being the x-axis, it's y equals negative 3. 3 units below the x-axis. And so now from there it goes up 3 just to the x-axis and down 3 to y equals negative 6. So again, what you have is 4 constants that come into play with these functions. The first constant, we'll call it A, is the coefficient of the sine or cosine expression itself. So now if we put that in front of, say, sine, I'm going to get rid of both of these now too. And let's pick up sine. Y equals sine of bx minus c. Close it, whoops. Close the parentheses. Yeah, and then put plus d. No, not capital D. Yeah. And we can create sliders for all these. If A, B, C, and D are all equal to 1, then you just have y equals sine of x minus 1 plus 1, and that raises this vertically by a unit. So instead of going between -1 and 1 vertically, it goes between 0 and 2 vertically, and it's also shifted to the left exactly 1. From instead of starting at 0, 0 and going up, it's starting at -1, 0 and going up. But for instance, if we let C be 0, let's see if I can get that right here, yeah. And if we let D be 0, there, now we just have our basic sine wave. A is 1, B is 1, and C and D are 0. So there's y equals sine x. And we can play with the amplitude by altering A. And notice if I make it more and more positive, it increases more and more up and down. But if I go to make A negative, watch what happens. It just flips over, it reverses. Now starting at the origin, it's going down instead of going up. So let's go back the other way again. With A positive, it goes up. With A negative, it comes down. And what happens if we, let's just make it -2. There. And what happens if we add a D? Right now D is 0, but if we add a D, it just causes a vertical shift upwards or downwards. The whole graph moves up or the whole graph moves down. That's pretty nice. These slider functions with Desmos are very nice too. And notice how to accomplish this, all I had to do was insert these constants in here at any place I want in my equation, and it automatically prompts me, Desmos does, do I want a slider for each of those constants? And I said, yes, I did. And so now we really get this nice little tool to work with here. And what if I change the C? The C causes a horizontal shift, what we call a phase shift with trig functions, causes a horizontal shift when C, you see what's happening there. As C increases, remember C is what's being subtracted from the x term, so as C increases, you're making a more and more of a negative number after the x, so it moves it more to the right. And if you go the other way, if C goes negative, a negative number being subtracted from x is a positive, so that causes it to, yes, go to the left. So, I hope that's all been instructive and helpful. And let's just conclude this with a closing point here. Let's see, where is it? Horizontal translation. It's in here somewhere. Yeah, right here. Final type of transformation, and we just talked about it, the vertical translation caused by the constant D in these equations right here. I suggest these two equations in your textbook on page 437 should be in bold letters in their own little box, because you're going to want to come back to these equations again and again, but here they are, just sort of stuck in the middle of nowhere in your text, but I'm pointing it out to you. This has all four of the constants that affect the graphs of sine and cosine functions, the A, the B, the C, and the D. And again, the A is the coefficient of the sine expression or the cosine expression, and A determines the amplitude. The amplitude is the absolute value of A. Then the B is always the coefficient of X inside the parentheses of what you're taking the sine of or the cosine of. So B is the coefficient of X, and it's related to both the period in that the period equals 2 pi divided by B. It's also related to the phase shift, which C is itself related to. C is the number subtracted from the X term. And C divided by B is the amount of phase shift. And finally, the constant D, just as it is, plus or minus, is the amount of vertical shift. So if D is positive, it's a vertical shift upwards that many units. If D is negative, it's a vertical shift downwards by that many units. And that concludes the lesson on the graphs of sine and cosine functions. If you have never seen Desmos before, I certainly hope this has been helpful to you, and you make use of that. And by the way, you're always welcome to use Desmos as a tool. You can certainly use it on your homework. You're allowed to use it on online tests in WebAssign. You're allowed to use it on the proctored midterm exam and the proctored final exam. Desmos is always available to you to be used as it's helpful. So, concluding the lesson once again, I certainly hope this has been helpful, and have a good rest of the day here.